Right now, invisible rivers are dragging entire galaxies off course. They are gravity wakes in dark matter, plus magnetized gas flows. The immediate takeaway is simple: space is sculpted by hidden engines. These engines run everywhere, even in regions that look empty. They push, pull, heat, cool, and shuffle matter across time. Follow them, and the universe stops seeming random noise. You can predict shapes, histories, and futures from their fingerprints. Two spirals pass each other, their star fields glittering like frost. They do not fly cleanly apart after the near miss. A drag builds behind each galaxy, thick as cosmic syrup. That slow drag is called dynamical friction, a gravitational wake. It means motion through a sea of matter creates its own break. This matters because orbits decay and galaxies end up colliding. Stars barely touch, but their halos lock and bleed momentum away. Mechanically, every massive clump focuses background particles into a trailing overdensity. That overdensity tugs backward, stealing kinetic energy over millions of years. Friction grows stronger in denser regions and with slower relative speeds. Rule of thumb: big things break faster than small things. Our Milky Way and Andromeda feel this break right now. Their halos already overlap, whispering a slow countdown to merger. In about 4 billion years, their cores will finally meet. Before that, tides will stretch arms into long, starry bridges. Gas will compress, ignite starbursts, and feed their central black holes. Simulations show the wake clearly, rippling like a ship's foam. Example: in real terms, satellites sink inside clusters within a few billion years. So the picture is, gravity carves paths and then erases them. Stretch the camera far out until galaxies look like glowing pollen. You see filaments, knots, and vast dark basins between them. That grand lattice is the cosmic web built by dark matter. Dark matter means mass that bends gravity but barely interacts with light. We care because this skeleton decides where gas can gather and cool. Gas follows the web, not the other way around. Gravity pulls along filaments and funnels material into growing nodes. Overdensities expand slower than the universe, so they keep catching more. Tiny early ripples inflated, then amplified through relentless gravitational instability. Simulations seeded with slight noise reproduce the same foam-like structure. Add only dark matter, and the scaffolding already leaps into view. Pour gas onto it, and galaxies light up along the threads. A single filament can span tens of millions of light years. Clusters sit where many strands cross, like knots on a net. Quasars backlight the web, exposing hydrogen as a spectral picket fence. That fence is the Lyman alpha forest, mapping density along sightlines. One sentence recap: structure forms where the dark skeleton is thickest, so galaxies inherit positions, spins, and fuel from this hidden framework. Net result: the web quietly scripts the universe's large-scale story. Now drop into a galaxy's core where the night turns electric blue. A black hole sits there, small in size, huge in influence. When gas falls in, the core brightens and launches fierce jets. That pushback is feedback, energy returned to the galaxy's own fuel. Why care? It decides which galaxies keep forming stars. Too much energy, and gas stays hot, buoyant, and unwilling to collapse. Too little, and cooling runs wild, dumping fresh clouds into spirals. Mechanically, jets inflate bubbles in the halo, stirring and heating plasma. Shocks ripple outward, while turbulence redistributes heat like a slow mixer. Radio lobes carve cavities thousands of light years wide. Meanwhile, cold filaments can still rain down along narrow paths. Observations of MATI-7 show bubbles rising like smoke in dawn air. Those bubbles carry about 10 to the 54 joules. That is enough to shut down a galaxy's star formation for ages. Example: in real terms, clusters need continual heating every 100 million years. Otherwise, their cores would catastrophically cool and trigger runaway starbursts. Bottom line: black holes regulate their cities by throttling the gas. Swing to a spiral arm where dust lanes twist like braided rivers. Threads of magnetism run through that gas, quiet but persistent. A galactic magnetic field is weak, yet surprisingly organized. It shapes how gas flows, clumps, and resists collapse or shear. We care because it controls star formation efficiency across time. Charged particles spiral along field lines, not straight through space. That redirects pressure, spreads heat, and couples clouds across kiloparsecs. Turbulence then tangles the field and also gets guided by it. Together they form magnetohydrodynamics, the traffic rules for cosmic fluids. Polarized radio light sketches the field like invisible contour lines. Faraday rotation twists signals, revealing strength, direction, and coherence. In the Milky Way, typical fields measure a few microgauss. That is about 1,000,000 times weaker than a fridge magnet. Yet over thousands of light years, that whisper can move mountains. Rule of thumb, weaker forces win when they act for longer. Antenna arrays map swirls over time, catching eddies as they fade. So the takeaway is, magnetism quietly budgets energy and motion. Fade to the first dawn when the universe still looked foggy. Young stars ignited and their light began scrubbing the fog away. That fog was neutral hydrogen, opaque to energetic ultraviolet photons. Reionization is the era when that gas got stripped of electrons. This sets the transparency of space and the fate of small galaxies. Photons push on dust and gas, adding a gentle outward pressure. Near bright clusters of stars, that push can clear whole cavities. On larger scales, ionized bubbles grew, overlapped, and finally percolated everywhere. We trace this history with the cosmic microwave background's tiny polarization. We also count distant galaxies and measure how much light escapes. By redshift 6, most space was ionized, and sightlines opened wide. Some pockets lingered neutral much longer, hiding behind thicker walls. JWST now peeks into that twilight, weighing early stars and dust. Example in real terms, a massive cluster carves a 1,000 light-year hole. Within 10 million years, radiation pressure sweeps and thins its nursery. So the picture is light does sculpt, not just illuminate. Now watch a starburst galaxy, glowing red in X-ray halos. Its core is frantic, birthing stars and detonating supernovae constantly. Cosmic rays flood out, along with tangled magnetic fields and hot gas. Cosmic rays are near light-speed particles, mostly protons and electrons. They add pressure that does not cool like regular gas. That extra push can launch galaxy-scale winds into intergalactic space. This shapes metal budgets, gas reservoirs, and future star formation rates. Outflows also throttle central growth by starving the inner reservoirs. Lines of sight show blue-shifted absorption, proof of gas rushing out. Velocities reach thousands of kilometers per second in extreme cases. MADI 2 shows a bipolar fountain, its chimney stretching tens of kiloparsecs. Simulations need cosmic ray physics or winds stall too quickly. Rule of thumb, more supernovae means stronger, longer-lived outflows, but winds can also fall back later, raining as galactic fountains. Fresh infall from filaments then mixes, renewing disks and bars. What to remember, high-energy particles steer how galaxies breathe. Tilt toward a massive cluster, where background galaxies stretch into arcs. Gravity there acts like glass, bending and magnifying passing light. Gravitational lensing is the deflection of light by mass. We care because lensing lets us weigh things we cannot see. It also reshapes our view, revealing tiny sources otherwise invisible. Light follows curved spacetime, taking longer, brighter, or duplicated paths. Strong lensing draws rings and arcs like neon on velvet. Weak lensing shears many galaxies slightly, in correlated directions. That shear maps the dark matter across megaparsec scales. Time delays between images reveal distances and expansion rates. Some systems echo flickers, arriving days or weeks apart. The frontier fields exposed background galaxies at record faintness. Numbers help, magnifications can exceed 10 for lucky alignments. Lens models reconstruct sources, testing how clumpy halos really are. So the takeaway is, gravity edits the universe's pictures for us. Those invisible rivers were not magic after all. They were gravity wakes, magnetic threads, radiation, and high-energy winds. Each left marks you can spot once you know the cues. Follow the web and you predict where galaxies will bloom. Watch the cores and you learn who grows and who starves. Track the light's bends and hidden mass steps into view. Net result, space looks alive when you watch it over time. If this sharpened your cosmic instincts, share it with a friend. I will keep digging into the quiet engines that run everything. See you in the next one, under the same dark sky.